All right, so it turns out that one of our tutors also answered this question, and so I'm going to share their response in this video. Fortunately, he answers the question in a very different way, so I think it'll be very enlightening to see both of the responses.
Hi, thanks for your question. So first of all, what is an inverse matrix? So matrix A will take something like X, a vector X, and this is the input. And what A does is it converts it from the input to the output in a specific way. So given a specific input X, you're going to get, putting it through A, and you're going to get a specific output Y. Not Y, B. So specific input X gives you specific output B. And if you change the input, you're going to change the output in different ways. You might not even change the output, depending on what A is. It all depends on what the matrix A actually is. But matrix A will tell you the rule from changing the input to the output, essentially. And so now that we know that, what does A inverse do? So here's a graph, okay? Let me just draw this out. And here's the red, and that is the input. And blue is the output. Okay. So red and blue are vectors. So here's A inverse. And I'm going to draw the same red and blue. Now the difference is, in A, in the first graph, we're going from red to blue. But with A inverse, we just simply go backwards. We just go from blue to red. And that's all it is. That's a very conceptual way of thinking of it. But if we look at more of the mathematical side, so the file that you attached had this problem, right? So it was referring to something called the difference matrix, which is right here. And this is equal to A, okay? So with this matrix, we can start with something like x equals 1, 2, 3. And we can put it into A. And then at the output side, we get the differences of each of these things. So just 1, 1, 1. Okay. Now, thinking about the analogy I made up here, right? Let's try to predict A inverse, right? And we maybe don't know what actual A inverse looks like yet. So these numbers we may not know. But what we do know is that if I put in 1, 1, 1 to A inverse, I'm going to get 1, 2, 3. And you may be saying, okay, that's great, but how do we actually find the numbers? Which is a very important part of it. And there's actually several ways to do that. So I will address that in part 2. All right, so in part 2 of this video, I'll go over the two main methods. There's two main methods to find an inverse matrix. So starting with A, we'll just do the same one. So 1, 0, 0, negative 1, 1, 0, 0, negative 1, 1. That'll be A. Okay, the first method is really, really similar to Gauss-Jordan elimination. Gauss-Jordan elimination. And you may have seen this method already. It's a really common method to basically solve systems of equations pretty quickly by hand. So what we do is, first of all, we're going to do the left bracket. And then we're going to write out the matrix. 1, 0, 0, negative 1, 1, 0, 0, negative 1, 1. And then we're going to draw a vertical line. And on the right of the vertical line, normally in regular Gauss-Jordan elimination, what we would put here is the B vector, right? But that is not what we're going to put here this time. To find the inverse, we can actually do something really cool. We're just going to put 1, 0, 0, 0, 1, 0, 0, 0, 1. And that is the identity matrix. So we put the identity matrix on the right side, and then we can do Gauss-Jordan elimination. So I'll just quickly go through that here. Okay, so I did the Gauss-Jordan elimination. It's 2 steps. So the first step, I added the first row to the second row, and then made that the new second row. And then the third step, or the second step, I did row 3, and then I added row 2, and I made that the new row 3. And after those 2 steps, we see that on the left side, we're left with the identity matrix again. And take a look at what we have on the right side. We have a new matrix. And if you remember from the thing in the file you sent me, your notes, it's the sum matrix. So that just shows that this method gives you the inverse of A. So yeah, basically this is a really sort of simple method of finding an inverse. You just put the original identity matrix on the right side, and then you put your original A matrix on the left, doing Gauss-Jordan elimination, and then what you end up with on the right is going to be A inverse. Okay, so that's the first method. So the second method is a lot more complicated, but it is a lot faster. Which doesn't sound like it makes sense, but trust me. So adjoint method. Okay. So in this method, there's 1, 2, 3 steps. There's 4 steps. Okay. And let's just use a 3 by 3 matrix. We'll use the same one. Okay. So 1, 0, 0. Negative 1, 1, 0, 0, negative 1, 1. We're just going to use the same A matrix. So this is a 4-step process. Step 1, we're going to find what's called the... Okay, it's actually a 3-step process, but the first step is basically 2 steps. So you'll see what I mean. So I'm going to say step 1 of 3 steps. Step 1 is find the cofactor. Actually, it's the cofactor matrix. So I'm going to split this up. Step 1.1 is take what's called minor. Just minors. I don't know. I don't really know if it's minor coefficients or something. It's just the minors. Take the minors. And what that is, so for each minor, what you do is each number in the original matrix has a certain position. So that 1 in the upper left is in the first row in the first column. So what we're going to do is we're going to cross out whatever row and whatever column it is, and then we're going to take the determinant of the rest of it. And if you know how to take the determinant of the rest of this matrix is going to be 1 times 1, and then minus negative 1 times 0 is actually just going to be 1. Okay, so the first one, and here, this is the matrix of minors. Matrix of the minors. And we're going to keep track of all of the answers down here. So in the upper left, we get 1, because that is the determinant of the rest of the matrix when you get rid of the same row in the same column that you're looking at. And so we're going to do this for all of the elements. So all of the positions of the matrix. We're going to do the same process. So for the second one, let's do the middle top, okay? So for the middle top, we're going to be, and I'll just erase to make this a bit more clear, for the middle top, we're going to be crossing out the same row and same column. And so what we're left with is going to be this -1, 0, 0, 1. -1, 0, 0, 1. Because we crossed out the top row and the middle column, and that's what we're left with. And to take the determinant of that, we're going to get -1. And that -1 is what goes here. Now, the third one, we're going to do the top right, and it's going to be a similar thing. We're going to cross out the right column in the top row, and what we're left with is -1, 1, 0, -1. So I just made the changes over here. Now the determinant of this is 1. And that's what goes here. And so for each one of the numbers in the original matrix, we're going to do that exact same process. Cross out the same row, cross out the same column, take what's left of the matrix, and then put it in a smaller matrix, which will be 2 by 2 in this case, and then take the determinant of that, and that's what goes in that position. So for the fourth one, and I'll just cut, and when I'm done, I'll just show you what I got for this step. Okay, so this is what I got for the matrix of minors. So hopefully you can see why it's called the matrix of minors, because to get this matrix, you're basically taking the determinants of like smaller matrices. So like basically that's why it's minor matrices. So now that that's we're still on step 1, and we actually still have another part to step 1. Like I said, step 1 is basically 2 different steps. So the second part of step 1 is going to be a lot easier. So don't worry, this is just getting easier from here. And what we do is we're going to change some of the signs. And by some of the signs, I mean we're going to change these specific signs. Now what did I just draw? A lot of pluses and minuses. And where there's a minus sign, we're going to change the sign of that position. And where there's a plus sign, we're going to keep it the same. So what we get using this rule, 1, 1, 1, 0, 1, 1, 0, 0, 1. This is the cofactor matrix. All right, and now we're done with step 1. Just a word. This process works with 3 by 3 matrices, 4 by 4 matrices, any size of matrices as long as it's square. So as long as it's n by n, or the same height as width, this process will work. And that's I wanted to mention it because this checkerboard pattern of plus minus plus minus plus minus plus minus plus would apply to any size. So like, let's say we're doing a 4 by 4. So this is just an aside. Let's say we're doing a 4 by 4. The pattern would be plus minus plus minus minus plus minus plus plus minus plus minus minus plus minus plus. And so the commonality is that this plus is on the top left always, and we have a checkerboard pattern throughout. And what that means is that the diagonals also all going to be pluses. But you see the pattern. So anyway, we're done with step 1. We have what's called the cofactor matrix. Okay, so step 2 is actually really easy. It's called the adjoint. We're going to get the adjoint matrix. And you may recall that is the method, the adjoint method. So we're going to get to the adjoint matrix now. So we've made a lot of progress. Okay, but the adjoint matrix is actually really easy because all we have to do is take the cofactor matrix and then take the transpose. So let's call the cofactor matrix C. and then this is ADJ. It's just going to be C transpose. So, for example, in this one, here's our cofactor matrix. And then here is the transpose. So we just flipped it over the diagonal. We just flip it over this, flip over diagonal. And that's how we get the adjoint matrix. Okay, and now we're just going to do the third and final step. And the third step, which is a bit harder than step 2, but a lot easier than step 1, we are going to take the determinant. So take of the original matrix A. Okay, so I'll quickly do that. In fact, I'll just walk you through the process of taking it, just because taking a determinant is also a little bit tricky in its own self. So to take the determinant, we're going to do the same process sort of we did with the minors process up here, which what we're going to do is basically go across a row. We're going to go across this top row, and we go, and there's many videos about how to take the determinant of a matrix. This is a fairly tricky process. So if you don't understand what I'm doing, I highly encourage you to go look up any of the myriad videos that are online, that are on YouTube. Khan Academy has many great examples of this, and also you will probably learn this in your class if you haven't already. So for now, I'm not going to take the time to explain every step of this, because there are already tons of great resources out there who do that much better than I will. Anyway, I'm just going to take the determinant going across the top row. So what we do is we go, first of all, it is the first of the top row, which is a 1, times the determinant of 1, 0, negative 1, 1, which is this thing right there. Okay? And then minus the second element of the top row times the determinant of whatever we would be left with taking out the same row and column. So negative 1, 0, 0, 1, which of course comes from there, as that's what would be left. And finally, we're going to do plus the third element in the first row, which is a 0, times the determinant of negative 1, 1, 0, negative 1, which is what would be left of taking the same row and column out. So that. And all in all, once we do all of this, determinant of this is 1, determinant of this is negative 1, determinant of this is 1. So we're going to do 1 times 1 minus 0 times negative 1 plus 0 times 1. And all together we get 1. Which is the determinant of A. And finally, this is actually what step 3 is. And this gives us the final answer for A inverse. And is 1 over determinant A times the adjoint matrix. Which is 1 over 1 times our familiar matrix. And we know what we get. Just basically rewriting it. Because since the determinant was 1, doing that whole determinant thing actually didn't change anything. So that is our final answer. And that is how you find an inverse. It's a tricky process. I personally think the Gauss-Jordan method is way easier. But when you get to higher order matrices, 7, 8, tons of stuff like that, computers actually find this long and complicated adjoint method much easier, which is why it's taught. I guess it's why everyone uses it. So yeah, in summary, there's two methods. Gauss-Jordan elimination will find you that inverse matrix really easy. You just take the identity matrix, put it on the right, and then you put the original matrix on the left, and you do a couple steps and you get there. Adjoint method is very complicated and people have trouble with it, but the strength of it is that it will never give you a wrong answer. And you always know how to do it. Now that we've seen how to find an inverse matrix, just a quick last word on why this is useful. So let's say we have a system of equations. Ax equals b. B is known. We know what b is. But x is unknown. Okay. And we want to know what x is, right? And so by the way, a is also known. This is a classic system of equations. Now, a could be any dimension, x could be any dimension, as long as it's a square matrix. As we'll see, we'll only be able to take the inverse of a square matrix, and we're going to be using the inverse as a way to solve for x. But anyway, as long as a is a square matrix and x has the same dimension and b has the same dimension, this will always work. As long as A is invertible, because there are some matrices which are not invertible, as we'll see. So just a quick note on that. Some matrices are not invertible. And the reason that's the case is if we think back to our adjoint method, we see that A inverse is equal to 1 over the determinant of A times the adjoint matrix, ADJ, if you remember back to the last part. So this will always work unless determinant A is 0. If determinant A is 0, then we can't do this. It's not invertible. Anyway, that's why some matrices are not invertible, because sometimes the determinant of A is 0, and then you're out of luck. You'll have to find another way to solve the equation. And for now, let's just say A is invertible, and the determinant of A is not 0, and we can find the inverse. So here's what we're going to do. We're going to multiply both sides of this equation by A inverse. So there's a rule in linear algebra that says you can multiply both sides of something that's like an equality, and you can multiply it by like the same thing on both sides, but like it has to be on the left. So actually doesn't have to be on the left, but usually it's done on the left. So you can see we put A negative 1 on the left of both sides and multiplied it. And there's another thing basically that says that if you're multiplying matrices together, it's commutative. So that means A negative 1 times AX, where AX is in parentheses, is equal to A negative 1 times A times X. And you may even be able to see where this is going, because there's also another rule in linear algebra that says A negative 1 times A is equal to I, which is the identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And so all of this together, here's what we get. A negative 1 times A times X. I times x equals a negative 1 b. And what that gives us is I times something just gives you the same thing. So x equals a negative 1 b. And that's why this is useful. Or that's one of many reasons why it's useful, but it's the most like basic and sort of like you'll use it a lot. So if you want to find an unknown for x, you just have to do a negative 1 times b. Starting from here, the answer to x is going to be this. All right, that's it for the I guess response. Hope that helped. And yeah, thanks for watching.